Welcome. Today we will begin our statistics unit with the notes worksheet entitled Describing Quantitative Data Graphically and Numerically Day 1. We'll investigate a few data sets today and talk about ways to mathematically describe the values in those data sets. So let's start at the top here. Just very simply, as mentioned, today begins our unit on statistics. So I guess just a very quick definition of what we would entitle statistics here. So statistics is the science of data, the analysis of data, making sense of data. And so we'll go ahead and do that from a couple different vantage points today. We'll do it just quickly from a visual representation, and then certainly most of the notes worksheet will be from a more numerical representation of data. So just a couple definitions to kind of put in place here. When we look at data set up graphically, and we could do that with a dot plot, actually as you see here on your sheet, a couple dot plots, stem and leaf plots, box and whisker plots, histograms. What we want to do is just describe the shape in very general terms. So a couple of the types that we would see would be either symmetric or skewed. And so let's go ahead and jot a couple things in here and then play a little compare and contrast if we get a chance. So symmetric would be where the right and left sides of the graph are approximately, and again it doesn't have to be precise, but approximately mirror images of each other. So if you can jot that in for me, that would be great. All right, not too bad. Whereas when we have a skewed, and we'll actually see skewed from the two directions there, left skewed and right skewed, here's what I would put in, and if you could do this as well, that would be great. Where one side containing half of the observations is much longer, I'm sorry, we're going to have to go below here, is much longer than the other side. All right. So as you can see on your paper, I have two dot plots, and we'll talk about the data sets that they represent momentarily, but essentially two dot plots, and I would argue that one is fairly symmetrical in nature, and one is skewed one way or the other. Again, we'll talk left versus right in just a minute there. So see if you can kind of figure out for yourself there which is which, and then I'll go ahead and jot a couple things down. Okay, well what I have is this left one over here. It says dice rolls underneath. So this occurs when we look at rolling two dice and then calculating the sum. So for example, when you get a 1 and a 1, the sum would be 2, and you could see that happen a couple times, all the way up to getting a 6 and a 6, where the sum would be 12, and you could see there are a few right up here. Now the most common one happens to be 7, and so this would be a sum of a 7, because there are different ways to get 7. You can get a 7 through a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. So different ways to get 7, so that is the most common sum that comes up when you roll two dice, and so you can see that right here that this has the greatest frequency. So I guess the argument can be made, to make a long story short here, is this would be the symmetric one. And so you can see that essentially the left side and the right side of the center are approximately mirror images of one another. Are they perfect? No, not by any means, but they are approximately mirror images of one another. So let's go ahead and just write symmetric right in there, which obviously makes the other one skewed. And I guess I would ask you this as we look at this one here. I believe these would be like test scores in a particular class or something like that. Do you think that this would be left skewed or right skewed? And I guess if you take a look at this, and I wrote this on my sheet, I'm going to put this in. I believe there are 30 data points in this particular set here, and I think that's kind of the halfway mark. So I think we have, if I have this correct on my sheet, 15 observations to the left of my demarcation right here, and then 15 observations to the right for the total of 30 scores total. So jot that in if you get a chance. And you can kind of see that the 15 observations to the left are quite a bit more spread out, are longer than the 15 observations to the right. And that's what it says right up here. one side containing half of the observations, and that would be the left side, is much longer than the right side in this particular case. So I hope everybody would be in agreement with me that this is what we would call left skewed. It is sort of elongated out to the left. Okay, so again, just kind of putting that in place. Won't make too much of a federal case about it there. We might see this over the course of our unit a little bit, so we just want to be a little careful with it. Okay, good. Let's get into our next piece. So what we're going to do is describe data with numbers, and really there are two measurements that we're going to focus in on. The first one is what we would call the center, sort of a typical value for the data set. And one way to measure the center, or the typical value in the data set, would be what is called the mean. And so let's go ahead and put this in place, what I have on my paper here. This is going to be the notation that we use, and this is what's called X bar. So you'll see me use this over the course of the unit. So X bar is essentially the arithmetic average of the observations. And I think you probably knew that coming in, but we want to be pretty formal about it if possible. So X bar is the arithmetic average of the observations. And of course what that would look like, just kind of put this in here rather than setting it up as a separate formula. But basically we would take all the data sets, all the way up dot, 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 all the way to the nth term, and obviously divide by however many there are. So we get the sum of the data sets, data points I should say, and divide by however many, divide by n. Okay, and I know you can do this. I'm not too concerned about this piece. Obviously we want to see this in the context of our entire unit, so we'll just start out nice and easy getting the mean. And so let's go ahead and take a look, example 1 here. So the following data set shows 20 travel times of Mr. Meyer biking from Boulder High School to his house. So when I ride from Boulder High to my house, I calculated 20 times. I've got a little timer on my bike. And so these are the number of minutes that it would take to go from Boulder High to my house. And so what would be the average or the mean biking time? And again, I don't think we need to waste a ton of time on this, to be honest. I know you can take all of these and add them together. And after you add them together, you would divide by 20, of course. So I guess for our purposes here, I'm going to write a little n above that. So that's our n value. And again, I'm not concerned. I know you can do that. So let's just go ahead and write what I have. And we'll go right on to the next piece. So if you were to find the sum, add all those together, of course, I get 694.98. And as mentioned, divide by 20. And so the mean biking time, a typical biking time, would be about 34.749 minutes, give or take. Perfect. Again, add them up, divide by however many values are in the data set. Okay, not too bad, right? Let's go ahead and maybe do one more here as well. So I did a quick poll of 21 teachers in Boulder High School, and so these are their ages, so 21 different data points in this set, and determine the mean age. Again, not that big of a deal here. So what we want to do is add them all up. I'll do the same thing. I know you can add them all up and divide by however many, so not too concerned about that piece. So let's just do a little X bar right there. And in this case, if you add all those numbers together, the sum turns out to be 881. So just jot that down. And if you want to go ahead and double check on me, that's fine. And in this case, divide by 21. So 21 teachers at Boulder High School. And if we want a typical age for this particular data set, in this case, the mean happens to be about 41.95 years old. Okay, good. So one way to calculate the center, or a typical data value, would be the mean. And as we said, that's the arithmetic average of the values. All right. Well, another way to measure the center is using what is called the median. And so we'll go ahead and put this in place here as well. So I'm going to use a capital M to notate the median there. So the median is the midpoint of a distribution half the observations are smaller than the median, and of course, the other half are larger. And so probably have to come down here, that's all right, than the median. So a value right in the middle of the distribution. So again, median is essentially middle. All right, well, we're going to use the same two data sets here on the next piece, so let's go ahead and get that going. And so mean for the center, median also for the center. And so example 3, it says determine the median for the data sets in examples 1 and 2. So what I did is I took the biking times, put them here. Ages of the teachers at Boulder High School, put them here. And I am a very nice guy. For your convenience, the values have been arranged from smallest to largest. So if we're going to find sort of the middle value there, obviously what we want to do is arrange them from smallest all the way to the largest. That way we can find that middle term pretty easily. All right, so I did that for you. That was kind of me. Why don't we go ahead and just see what we can do with this. Now, the reason I kind of put two data sets in, and especially the way I did it here, is you'll notice that there are 20 data points in this distribution and 21 data points in this distribution right down here. So there are a couple different ways we have to do this based on depending if n is even or odd. Okay, so let's go ahead and put this in. And we just have to be careful in this one especially. When n is even, like the biking times, what we want to do, because there's no primary middle term, essentially what we want to do is take the mean of the two middle terms. So if we kind of work our way towards the middle, starting at the smallest and largest, work our way towards the middle, we don't get to one value right in the middle. We actually get to two values right in the middle. And so as a result, we want to take the mean of the two middle values. So put that in if you would. And then let's go ahead and figure out what those two middle values are. Again, if you kind of work your way inward, starting at the smallest and the largest, and just counting inward here, I believe what we have is sort of the two middle terms would be these guys right here. Okay, so those would be the two. It looks like the 10th and 11th. And so what we want to do is go ahead and find the mean of those two values, and that essentially would be the median. Okay, and as a result, when we get our median, half the values will be less than that median, and half the values will be more than that median. Okay, so the median would be, in this particular case, the 35.25 plus the 35.33 and divide by 2. So I think I could pull this off here. So if we go ahead and add those, and you're more than welcome to grab a calculator, by the way, but if you go ahead and grab a calculator and do that calculation, I think we're going to get 35.29 minutes on that. So I'm going to box that up right there. That would be our median, so 35.29. And as you can see, obviously we would have 10 values below that median, and then 10 values above that median. And so this would be considered the center value if we use median as a way to represent. Okay, very good. If n is odd, it's pretty straightforward. All we just have to do is find the middle term. So I guess I'm going to write that here for you. N is odd, just find the middle term. All right, sounds good. So again, you just kind of start here and work your way in. It looks like if we have 21 terms, 10 of them would be to the left of the median, 10 of them would be to the right of the median, And so I believe we're focused on that one right there. See if you can see that piece as well. And again, that's why it's so nice that these were arranged from smallest to largest, because we can kind of just figure out what is the middle term from there. So again, 45 right here, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 to the left of it. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the right of it. And so that's our median right there. Okay, so not too bad. So 45 years old would be the median. And you can see, obviously, in this case that the median in each case is slightly different than what we got when we did the mean. So two different ways to talk about a typical value in a distribution, mean and median. All right, very good. So obviously, the next piece is just talking quickly about comparing the mean and median. So let's go back to a description of what we talked about at the beginning, the visual representation. So here's what I have, by the way, and then we'll go ahead and maybe see this in action a little bit. So the mean and median of a roughly symmetric distribution typically are pretty close together. And again, we'll see this off and on throughout our unit. So if we have a symmetric distribution, the mean and median typically are pretty close together. However, in a skewed distribution, and here's what we're going to see, I think, with at least one of these, then the mean is usually farther, let me get this straight for you, farther out in the long tail compared to the median. All right, so jot that down, and then hopefully we'll look at this, at least one of these data sets in a little more visual way. I don't think either one is all that symmetric, to be honest. I think they're both left skewed. If I remember correctly, though, this one is a little more left skewed than the other one. So we'll go ahead and kind of see that piece, at least visually, in just a sec. All right, so make sure you have that in, and then give me a minute here to just be a little visual with it, to really just emphasize this piece, and then we'll move on. So first and foremost, I guess let's go to the ages right there. And if I remember correctly, the mean for the ages, and you don't have to write this by any means, the mean was 41.95, whereas the median was 45. Sorry, give me just one sec on that. There we go. So you can kind of see they're a little different, especially you look at this data set right here. So the mean is 41.95, smaller than the median, which was 45 right there. So this one is to the left of this one by, you know, at least a few years there. And so what this should mean is that this is skewed to the left. It says the mean is usually farther out in the long tail than the median. Wherever the skew is, that's where the mean is typically going to go. So I have this data set already in the calculator here, if you can just give me a moment to kind of see this in action. So let's go ahead and see stat edit, and there are all the ages of the teachers. And so if I go ahead and put this together, I think I have it as a histogram. There it is. And I hope you would agree, just the way the calculator set this up here, that this looks to be a left skewed distribution, right? It seems like there are more values to the left of the center than to the right of the center. And if that is the case, if we want to measure the center via the mean, it's going to be further out on the tail. So again, the mean is roughly here at about 41.95, where the median, is at about 45 right here. So the mean is pulled out along the tail of the skew. If it's left skewed, then the mean is going to be to the left of the median. Okay. So I said it a couple different ways there. Hopefully that pretty much makes decent sense. We'll see this off and on throughout the entire unit. It's not a huge deal right now, but we do want to at least set the foundation for it. Okay, so one last time. In a left skewed distribution, obviously the mean will be to the left of the median. If this was a right skewed distribution, then the mean would be to the right of the median. Symmetric, they're virtually identical. Okay, let's go on to the next piece. So one way to talk about data is obviously to measure the center. And we have two different representations of the center at this point, mean and median. Another important way to talk about a distribution is the spread, the variability of the distribution. So for example, and this is going to sound kind of random, weather. As a matter of fact, if you were to go to San Francisco, California, the mean temperature in San Francisco is about 57 degrees, give or take. It just so happens that in Washington, D.C., the mean temperature is also 57 degrees. But is that a complete description of the temperatures in those two cities? The wardrobe that you would need to live in San Francisco is actually quite a bit different than the wardrobe you would need in Washington, D.C. Washington, D.C.'s weather is quite a bit more variable across the seasons compared to San Francisco. So the center, although a great description about a data distribution, it's not complete. So what we also want to talk about is the variability in that data set. And so there are a couple different ways to talk about this as well. The one way we'll talk about here, as you can see, measuring the spread of the variability, is what's called the interquartile range, IQR. And so here's what you're going to write in for me. So the spread of the middle half okay, get that in if you could, of the data between the first quartile, we'll talk about that momentarily, have no fear. So the first quartile is the median of observations to the left of the median and so it's, let me just make sure I have this right. So it's the spread of the middle half of the data between the first quartile and what is called the third quartile. Okay, so a lot of vocabulary coming your way here today and a lot of definitions. And of course, I think you could probably guess what the third quartile is going to be. It's the median of observations to the right of the median. Okay, very good. So we'll see this obviously in play here. It's one thing to get the definition, but we need to provide some context for it. So I've been focusing on really two data sets this entire notes worksheet. Biking times, for me, 20 of them, and ages of teachers at Boulder High School. So let's read example 4, and it also says provide a verbal interpretation for each. So it says determine the IQR in the two data sets and then go from there. All right, great. So first and foremost, again, very convenient for us at least, from going from smallest all the way up to the largest data value right there. I'm going to put this right in place right here, guys, sort of a little slash because it does talk about the median. So the median is, what did we say, 35.29 minutes. So that's the median right there. 10 values, of course, to the left, 10 values, of course, to the right. If we are going to talk about the spread here via this IQR, we do need the first quartile and we do need the third quartile. So the first quartile is going to be, as it says, the median of the observations to the left of the median. Okay, so here's the median, guys. Focus on that for a sec. There are 10 observations to the left. And so what we want is to find the median of those 10 observations to the left of that number right there. And so we count inward, of course. You know, we go 5 this way probably, and then 5 this way probably. Ultimately, the first quartile is going to be right in there. So I'm going to write that piece. Hope everyone's okay with that idea. So the median of those 10 values, and it would be right in between the 5th and 6th value. So I hope you would be in agreement that, of course, if we have a median that falls right in between two values, we take the mean of those two values. And so I'm going to go ahead and write this up here, what I have. So that would be taking the 33.83, adding the 34.21, and dividing by 2. So we talked about that before. And if we do that, we end up getting 3402. Okay, very nice. So the first quartile is going to be 34.02 minutes. Now the third quartile, based on the definition, again, not too bad here, guys. We've got 10 observations to the right of our median. We want the median of these 10 observations right here. So same deal, guys. We're going to probably go 5 this way and 5 this way. And again, hope you'd be in agreement that the third quartile is probably sitting pretty right in there. Okay, so again, unfortunately, the quartile ended up in between two values. So we have to do the same thing, and we're going to add those up and divide by 2. So if we do that, again, I know you can do these calculations. I'm not too concerned about that piece. We get right there as 35.92 minutes. All right, very nice. Okay. Well, guys, what we would do is talk about a way to measure the spread of this distribution right here. And the IQR basically takes the third quartile and subtracts the first quartile. So again, it's the spread of the middle half of the data. And so what we're going to do here for the IQR is subtract them. And so let's see what we get here. Let me just make sure I've got my numbers. 35.92 for the third quartile, everybody. How does 34.02 for the first quartile? And so it's the spread of what we would say is the middle half of the data. We're going to see this in a more visual light on the next notes worksheet. For right now, just strictly numerical. But I'm getting an IQR here of 1.9 minutes. Okay, I'm going to box that on up. And remember, it did say provide a verbal interpretation for each answer. So I'm going to go ahead and put this in place as well. And I guess this is what I would say when we talk about the variability, sort of the range or the spread of the values. So the range of the middle half. So we're not taking the range of the entire distribution. We're not taking max minus min. This way to measure variability or spread is to just talk about the range of the middle half of the values. So anyway, the range of the middle half of biking times, and that's what my values represent here, of course, is 1.9 minutes. Okay, so we have a center, and now we have a way to talk about spread or variability. Beautiful. Let's do it just on one more if we could, please. That would be great. And let's see what we have going here. So if you remember correctly on the ages, this was the median right there. So if you want to go ahead and just write big M equals right there. There's your median. And so if we want the first quartile, it does look like I have 10 to the left of it. Looks like I do have 10 to the right again. So I'm sorry, I don't have a ton of room here, but I hope you would be in agreement that the first quartile is right in between those two guys right there. And let's see this piece right here. It looks like 1, 2, 3, 4, 5, just getting my bearings. And then the third quartile would be the median of these terms, which would be right smack in the middle between the 48 and 49. So I'm going to just write a couple things quickly up here. I think we can all pretty much do this in our head. First quartile is equal to 34.5. Third quartile again, I think everyone would be in agreement that we would say it's 48.5. And so if we want the IQR here then, let's get that piece nice and easy. So it's the range of the middle half of the terms. And the IQR would be 48.5 minus 34.5. And so 14 years would be the IQR. All right, so again, it's a way to talk about variability rather than doing max minus the min to get the spread of the entire distribution. We talk about the IQR as being maybe a little better representation. Sometimes they're what are called outliers, which we'll see in the last piece, that sort of affect this, but don't really talk about the spread of most of the terms there. Okay, well, let's go ahead and quickly put this in place. Verbal interpretation, here's what I would say. Again, just to emphasize, IQR really represents the range of the middle half. So the range of the middle half of ages is 14 years. Perfect. Okay, very nice. Let's get into the last piece. One more vocabulary word to take a look at it on this notes worksheet, and we'll wrap up with one example here. So outliers. An outlier would be an observation that falls outside of the overall pattern. And so there's a way to numerically calculate if there's an outlier. And so here's what I have. So it has to be mathematically either more than 1.5 times, and here comes the IQR again, guys. So more than 1.5 times the IQR above the third quartile, or 1.5 times the IQR below the first quartile. So jot that in and we'll kind of see this in place. We'll see a couple different examples of this, so if it doesn't click on example 5, don't worry, we'll get another shot at it. All right, so last one here, guys. Let's see if we can put this one together. So here's what I'm going to do. If you remember, we had 20 biking times of me going from Boulder High to my house. And so what we're going to do here is add one more time, in this case 45.3 minutes. So this would be, say I got a flat tire and had to fix my flat tire on the side of the road. Obviously extended the time to take for me getting back home. So 45.3 minutes due to a flat tire and the time necessary to replace it. And so I've added that to my data set. So as a result, guys, now I have 21 values as opposed to 20. Okay, so I'm going to write a couple things here for this one just to clarify. So now in this case, I have 21 biking times. And just one thing I would note here, so because I added another biking time, the median, the quartiles, the IQR, all of that changes. Okay, and we're not going to go through the calculations again. I did it for you. So I do want to just be very clear about this, that if I do add another value here, then obviously that's going to change the median, and hence it's going to change these other representations as well. So here's what I'm going to say. I'm going to give you the necessary info, and then we'll go from there. So basically, this is the situation here. So the third quartile actually does change. I think it was like 35.92. Now the third quartile moves, again, because of this new data point right here. So the third quartile is this, everybody. The first quartile also changes, I believe. And so just want to make sure I have this on my paper. Just want to make sure I scribe it correctly for you. And that would be the first quartile. Okay, so let me just kind of label a couple things. You do it as well here. I'll get my bearings, you get yours, and then we'll go for it. So that's the third quartile, that's the first quartile. And so if I subtract them, of course, I get 2.065, and that's equal to our IQR. So mathematically, we do need the IQR. And so the IQR changes from, what did we have last time, about 1.9 minutes. Now the IQR is a little larger. The variability is a little greater. And so the IQR is 2.065 minutes. Okay, so I gave that to you. You would obviously find the IQR. Then what we want to do is see if there's an outlier. Well, this one, obviously, we would talk about it in terms of being above the third quartile. Obviously, a low value, we would then think about, is it an outlier below the first quartile? But this one's obviously large, so we're thinking about it from this vantage point right here. And so what we want to do is very simply take that IQR and multiply it times 1.5. So IQR, everybody, times 1.5. And in this case, I will bring it up on the calculator here. Let's get our value. So I have 2.065 times 1.5. And so that is what I get as my 1.5 times the IQR. Okay, so let's write that down. I think I saw 3.0975. All right, perfect. So that is what we want to look at in terms of above the third quartile or below the first quartile. And for a value like this, we're thinking, is that above the third quartile in a dramatic way? Okay, well, here we go. So here we go writing this piece. Quartile 3 is 36.085. That was given. And so 36.085 plus the 3.095. So, guys, that's the IQR times the 1.5. We add that on past the third quartile, and we end up getting only 39.185 minutes. So the question, of course, remains, is the 45.3, is that an outlier based on this right here? And the answer, of course, has to be yes. So 45.3 is far greater than this right here. Here is sort of the value, the demarcation here for what would be considered an outlier. Anything above this is an outlier. So anyway, yes, and in this case, by a lot. I got to get faster fixing those tires, I guess. So 45.3 definitely is an outlier. All right, that one took a little too much time at the end there, but hopefully the calculation, it makes sense. You'll get some help with this and some practice on this as well. All right, why don't I wrap it up right there, guys. Thanks so much for listening.